2, 3, 4, 6, 7, 8, 9, 10. Good morning, everybody. So, let's start our lecture today with proving that the free energy is the free energy. What do we mean by this apparently obvious statement? I mean that if you define the free energy by the partition function as this, then since in thermodynamics the free energy is U minus Ts, and S is equal to the derivative of the free energy with respect to temperature, right? So this is equal to U plus T dF dt, constant volume. Then you know that internal energy should be equal to F minus T dF dt at constant volume, right? But U is what? U is the internal energy, and therefore is the average of H, right? And therefore, in order to prove that this is indeed the free energy, we have to prove that this equality follows, okay? From our definition. If we prove it, then this is going to be the equivalent. I mean, it's going to be the free energy in the sense of thermodynamics. So, how do we prove it? Well, consider the fact that we had this definition. Sorry. So this is just a rewriting of this equation here, right? Okay, so now I can rewrite this as the integral dq dp over h to the 3n n factorial e to the minus beta h minus f equal to 1. I'm dividing on both sides by e to the minus beta f. Okay? Now, if I now take a derivative of this on both sides, I will get that, well, 0, because derivative with respect to beta. Okay? So I will get 0 equal to the integral dq dp over yes, over h to the 3n n factorial, and then I will have minus h, then plus f plus beta d beta f e to the minus beta h minus f. Okay? It's clear to everybody? Hopefully so. Okay, now beta d beta, so let's write it here. Beta d beta of something you can easily prove by changing variables, that is equal to minus t dt. of something. You just need to change variables from beta to t in the derivative. And therefore, this comes out to be equal to the integral dq dp of divided by h to the 3n n factorial e to the minus beta h minus f times f minus t dtf minus h equal to 0. And now if you look at this, this is exactly the equation that I wanted to prove, because this means that f minus t dtf times the integral over dq dp h to the 3n e to the minus h minus f, which is equal to 1, is equal to minus the expectation value of h is equal to 0. And therefore, we just proved the statement we wanted to prove, QED, quantum electrodynamics. Okay? All right. Now that we know this, so we know that this is the free energy, then it's clear how to play the game of statistical mechanics with the canonical ensemble. You just, compute the partition function. Compute the partition function. From the partition function, obtain the free energy. And then from the free energy, obtain everything else. Because from the free energy, you can compute what is the pressure, which is minus dF dV at constant temperature. You can compute what is the entropy, which is minus dF dt at constant volume, and then you can start playing with Maxwell relations, do all sorts of interesting things. Okay, it's up to you, but you can build all thermodynamics from this function, okay, of this particular system. Now, the canonical ensemble is an ensemble in which I did not fix, unlike the microcanonical ensemble, I did not fix the total energy. So I'm not sitting in a thermos. I'm rather like, well, it's slightly different. If you would close the door there, don't do it, I mean, it's not necessary, but let's imagine that the door was closed, then it would be more or less equivalent to us sitting in this room, because we can exchange through the windows heat with the external environment, but the number of particles and the volume of the room is fixed, okay, unless you get out, in which case we lose a bit of particles, some Avogadro number of particles. Anyway, so it turns out that even though these two ensembles are built for two different situations, if you're dealing with matter in the thermodynamic limit, which means that n goes to infinity, etc., but all the intensive quantities are kept fixed, then these two ensembles are equivalent. Okay? Now, in order to prove this, let me think if I do it now or do it later. No, I'll do it later. So, in order to prove that they are equivalent, one way to do it is you just prove that if you consider the energy fluctuations in the canonical ensemble, the fluctuations of energy, in the thermodynamic limit, when n goes to infinity, these fluctuations are much, much smaller than the average energy. And therefore, in practice, it's as if the energy was fixed. The energy probability is strongly peaked around some average value. And therefore, in practice, it's as if you were in the microcanonical ensemble. Okay? So the way to prove this is just a straightforward calculation. We go back to our definition of internal energy. If you go back to the notes to the calculation we've just made, look at this formula here, then this is equal to integral dq dp over h to the 3n and factorial e to the minus beta h minus f h. So this is equal to the internal energy, okay, to U. In other words, you can rewrite this as integral dq dp h to the 3n and factorial e to the minus beta h minus f h minus u equal to 0. Okay? Not fall asleep. Not fall asleep.
No,
Now we take this and we start taking, so we know that this is true, we start taking derivatives with respect to beta. Alright? Now if we take derivatives with respect to beta, what are we going to get? We get du d beta plus integral dq dp. Let's agree that when I write dq dp in between the parentheses, it means divided by h to the 3n times n factorial. Okay, this way I will not rewrite it all the time. So times u minus h, and then I have to take the derivative, so I will have f plus beta d beta f minus h e to the minus h minus f times beta. Okay, so here I'm acting, first of all I'm taking the derivative not of what I wrote before but of minus what I wrote before, so of u minus h. Then I first act with the derivative on u minus h. H does not depend on beta, u does depend on beta, and therefore I will get this term here outside. How comes you don't want to work? And then I will act with the derivative on the exponential and I will get out exactly what I got before. Okay? In the previous calculation. So this tells me that this is equal to du beta plus, now think for a second, f beta d beta f is equal to f minus t dt f, okay, which is equal to f plus tds plus ts, which is equal to the internal energy, is equal to u. Therefore, this is equal to integral dq dp of u minus h squared e to the minus beta h minus f. In other words, this is equal to d beta u plus average of u minus h squared. Okay? With respect to the canonical. But what is average of u minus h? So this has to be equal to 0. Now, what is average of u minus h squared? Well, this is equal to u squared minus 2 times u average of h plus h squared. Sorry, not this. Plus h squared. Okay, now it's correct. So this is equal to, now if you remember that u is just average of h, then this is equal to h squared minus h squared. So these are just the fluctuations of h, of the energy. Okay? So therefore this equation above, this one, let's do it in red, let's do it big. Now this equation tells us something important. It tells us that the fluctuations are, fluctuations of h, of the energy, average, are equal to minus d beta of u. Now what is the beta, minus d beta of u? If you do quick calculation, changing again variables, beta is equal to 1 over t up to k Boltzmann, which we take always equal to 1. From now on, we use the Silva units, okay? So k Boltzmann is equal to 1. And therefore, we'll get t squared dt u. But what is dtu? dtu is the heat capacity, right? So this is t squared times cv. And now cv is an extensive quantity, right? So it will scale like n. That means that if you now take the ratio of this square root, which I think is the standard deviation, correct? Is it correct? You're like me, you never learned what is the variance and what is the standard deviation. What is it? Standard deviation or variance? Standard deviation, right? I cannot remember it. I mean, it's amazing. But I cannot remember the names of my kids, so it's not something weird. Okay. So if you take this ratio, you will see that this goes, what stays above goes like square root of n. What stays below goes like n. And therefore this stuff goes like 1 over square root of n, which tends to 0 in the limit of n going to plus infinity. In other words, the probability distribution of the energy in the limit of n going to infinity is going to be infinitely picked around an average energy, which is given just by the internal energy itself. And that is why the two ensembles are equivalent. Now, there is another way to see the same thing, another proof. Which I like much more than this one, simply because it gives me a chance to tell you about something that is called the saddle point method. I don't know if you've ever heard this saddle point approximation of an integral. Only one, yes.
No, we did it in the class. Yeah,
you did it? Ah, you did it. Okay, perfect. Then
let's skip it.
I can skip it. Fantastic. Okay, so let's go back to this thing. dq dp e to the minus beta h. Now, this can be written as follows. I can write it as integral dE integral dq dp delta E minus h e to the minus beta h, or e to the minus beta e, for what it matters. Right? You see that I can certainly do that. Now, you see that this does not depend on h anymore. The only place where h appears is here. And if I take this integral here, this is what? This is what we called, in the context of the microcanonical ensemble, omega of E, right? It's just the derivative, is just what happens to the loacker when you squeeze it to zero width, okay? So it's going to be delta, big delta, times the integral with the delta function. All right, so this is equal to the integral dE omega of E e to the minus beta E. Now let me put this omega of E in the exponent. So this is dE e to the minus or plus beta t log of omega of E. Now the t here is needed to cancel the beta. Beta is just 1 over t. I'm forgetting about all k Boltzmanns. Minus h. And now this is what? This is nothing but up to a k Boltzmann that I'm forgetting, but it's there, is equal to the entropy, to the microcanonical entropy. So therefore this is equal to integral dE e to the beta ts of E minus h. Minus E, sorry, not minus h. Why did I write h? Okay, so now I have to perform this integral. Is it okay? Good. Now I have to perform this integral. Now, this integral is in the lucky form of an integral that can be done by the saddle point approximation. Okay? Why? Because both S and E are extensive. Okay? And therefore I can think of this, so let me make a green parenthesis, saddle point, set point. So it's the integral is in the form integral dx e to the n f of x. Okay? Now, it turns out that this integral, so if you think about this function here, this function is going to be dominated, this integral is going to be dominated by the points in which this function is minimum, is f of x. Let's say there is just one minimum for simplicity. Okay? And it's clear why it is going to be dominated, because this is an exponential function. So when this guy grows, you know, it's in the exponent.
We
so
need a minus.
it can be also plus, there's no problem. You want a minus? I put a minus. You can also have this. If you have a minus, you're right? I mean, when it's minimum, so you have to change between minimum and max.
Yeah.
So let me think for a second, because I'm always confused as. No, actually, I was wrong. When the other way around, it's dominated by maxima. And this way is dominated by minima with the minus sign. Okay?
Now.
Yes, it's dominated by minima. So let's stick to the minus sign. Okay, as you suggested. Let's plot this function. Let's say that f of x is like this. I don't know. It has a minimum around here. So this is x star. Then what happens? If you plot exponential of n of x, of minus n f of x, what happens is that here it's going to have the value e to the minus n f of x star. Okay? So let's say this is the value, e to the minus n f of x star, f star. But then the moment you deviate from it, this guy grows. And if it grows, it means that the exponential drop. But it drops exponentially fast. It doesn't drop as a power law. Which means that this function is going to look like this. It's going to be a function that is strongly peaked around this value. Okay? Strongly peaked around this extreme value. So now, how do I estimate this integral? It's clear that when I estimate this integral, the only thing I have to do is estimate what is the area around here. But the area around here is determined just by small fluctuations of this function f of x around this x star. Okay? So how do I do it then? I take f of x, I write it as f of x star, which is the extreme value, plus, and then I will have f double prime of x star divided by 2 x minus x star squared. I know that f double prime is positive because this is a minimum. Okay? And the first derivative is equal to 0 because it's a minimum. Now you plug this in here. And what do you get? You get that this is equal to integral dx of e to the minus n f of x star minus n f double prime over 2 x minus x star squared. In other words, this is approximately e to the minus n f star times some number, which are just the Gaussian fluctuations. What people call Gaussian fluctuations is just this Gaussian integral, integral dx, e to the minus n over 2 f double prime x minus x star squared. You see, this is the way it works. The saddle point approximation. Now, in order to do a saddle point approximation, you need to have a big number sitting here. Okay? Otherwise, well, it doesn't make much sense. Now, I'm going to tell you, but this is like, the things you heard from your grandmother and you didn't understand when you were kids, and you will understand in the future. So this saddle point approximation is essentially the way you go from quantum mechanics to classical physics, or is the way you go from statistical mechanics to what people know as mean field theory, or is also the way you go from quantum field theory to classical field theory. All right? So it has tons and zillions of applications in physics. It's very important, and it's better to understand it in detail just with one-dimensional integrals. You can apply it also to complex integrals and more complicated situations. This said, let's go back now to our beloved problem. So we have this integral, I wrote it here, and now I'm going to use the magic of technology to do something like this. Sorry. Paste. So we have to evaluate this guy. So we do it by the saddle point approximation. So we first take a derivative of the exponent with respect to e. Okay? And we get T ds dE should be equal to 1. This is what determines what is the minimum. And not surprisingly, this is again the condition of equilibrium. It's just, this finds for us an energy star for which ds over dE at E star is equal to 1 over T, right? Which is the usual condition of thermal equilibrium that we all know. And the second thing that we want to have is that this should be a minimum, and therefore we want to have ds, the way I wrote it, I'm taking the derivative of TSE minus E, and therefore I'm looking for maxima, not for minima. And therefore I want to have this smaller than 0. Okay? I want a minimum, not a max. Sorry, I want a maximum, not a minimum. Before, with a minus, you look for maximum. The other way. Okay? Great. Now, ds squared dE squared is equal to d dE of 1 over t, which is equal to 1 over t squared dt dE at constant volume, which is equal to minus 1 over t squared, the heat capacity. And this is obviously smaller than 0, right? And therefore what I get is that my integral, this guy here, once I do this saddle point approximation, is going to be equal to e to the e to the beta Ts of E star minus E star times the integral dE of e to the minus E minus E star squared divided by 2t squared Cv. So you see, usual story. Here what I have is, this is the free energy minus the free energy. So this is equal to e to minus beta times f. And then here I have the probability distribution in energy is essentially
You're clapping so much.
great. I mean, you know, whatever I say, I get a clap. It's fantastic. It's a dream. I mean, I'm the president of the republic. Anyway, so thank you. So you see, it's a No, why are you closing? I mean, this was my moment of... No, I'm joking. It's my moment of glory. So it's a Gaussian, the distribution, the probability distribution is a Gaussian with a width that scales like n. But now if I would rescale all energies by n, so use intensive energy densities, you would see that the width of this Gaussian would actually scale like 1 over square root of n if you rescale everything, and therefore would collapse to 0 in the thermodynamic limit. So this is essentially what is happening once more. Alright, so this said, ensembles are equivalent, everything is nice and beautiful, and now we can start. So I promised that I'm going to, you have seen zillions of cycles, and you're going to see zillions of partition functions in this course. So now we're going to start with the partition functions, and we are going to calculate tons of partition functions in the next few lectures. Okay? Don't be upset. I mean, you have to learn how to do at least one calculation, right? Okay, so exercise number 1. So let's see who is faster in doing this exercise, this super trivial exercise. Okay? I'm going to give you my Hamiltonian. It's just a single spin in a magnetic field.
High roller coaster.
It's, yeah, okay, fine. You got an ice cream. Fantastic. Okay, so what I want you to compute is the average energy of this guy at the temperature beta, and compute the limits for t going to infinity and for t going to 0 of the result. Okay? So let's see. Hyperbolic cosine is fine, but you have a coefficient in front. So let's see.
Two times hyperbolic beta h.
Yes. Okay, now compute the energy. But don't tell me the result. Let the others do it as well. Yeah, it's okay. 2 cosine probability. Now you have to take a derivative with respect to t and to beta. No, sorry, you have to take a derivative of the log.
And then you have to.
Yeah, but of the log, not of the partition function. Okay? What? No. Think about this is not a gas, right? So,
I don't want
yeah, it's okay, it's correct. Okay, let me, since I don't want to spend 3 hours on this exercise, let me explain, okay? Where's my pen? Thank you. All right, so when you're given a problem with the canonical ensemble, so the first thing you have to think about is what are my statistical variables, okay? And in this case, you just have one spin that can take 2 values, plus and minus 1, okay? Now look at the structure of the partition function itself. Here I wrote it for a gas of particles. Where is it? This. Now here I wrote it for a gas of particles, but at the end of the day, the only thing I'm saying is the probability to have my statistical variables, no matter what they are, they can be also spins, in a certain configuration is e to the minus the energy divided by t, divided by zeta, normalized, okay? And therefore the partition function is the sum over all possible configurations of my statistical variables of e to the minus h divided by t kvolts. Okay? So let's write it in words. So my partition function is equal to sum over all configurations of statistical variables of e to the minus beta h. Clear? So this is what it is. Now, if you're dealing with gases, your statistical variables are Q and P, or Q1, Q2, Q2, Qn, P1, P2, Pn. Okay? But if you're dealing with one spin, your statistical variables is just the values that this spin can take, which is plus and minus 1. So, for this particular case, therefore, this is going to be equal to sum over sigma equal to plus and minus 1, okay, of e to the minus beta h. In other words, is sum sigma equal to plus and minus 1 e to the minus beta h little h times sigma. But now you all know what this sum is. This is e beta h sigma plus e to the minus beta h sigma, or in other words, is equal to 2 cosine hyperbolic of beta h. Clear? Now you have a partition function. Now don't make the mistake of starting taking derivatives of partition functions, because the partition function is not a physical quantity. What is a physical quantity is the logarithm of the partition function, that is the free energy. Okay? Derivatives of the partition function itself, okay, do not make any sense.
But we can always write this as 1 over the partition function dc.
Yes, but conceptually it's important to keep in mind, you're right. I mean, you can, I can define f as minus t log z, and then every derivative of f is going to be a derivative of z divided by z. Fine. But it's important to keep in mind that the physical quantity is the free energy and not the partition function. Why, for example? Because in certain cases you might have to deal, for example, with disordered systems. Okay? With systems that are subject to some kind of disorder. In the couplings, in the energies, in whatever you want. And then you have to decide, when I take an average over disorder, what do I average? Do I average the partition function or the free energy? I average the free energy, because you always average over disorder physical quantities, and the partition function is not a physical quantity. So this is, well, there is some subtlety. You can take also an annealed average and then average the partition. Forget about all these subtleties, but it should be kept in mind that the partition function, so the free energy is the physical quantity. Anyway, once you have the partition function, the first thing you do is you compute what is the free energy. Okay? So this is equal to minus t cosine hyperbolic of beta h. And now you can take the derivative of the free energy with respect to beta and get
Logarithm.
log. Yeah, absolutely. You're right. And then there is a factor of 2 somewhere here. And then you can take a derivative of the free energy with respect to so the average energy is going to be equal to minus d beta log of z, and this will come out to be equal to minus h tangent hyperbolic of beta h. All right? Now you can ask yourself, whenever you get to a result in this kind of exercises, you want to ask yourself one question, in particular in the final exam. Is the result I got correct? Now, in this case, it's correct. I mean, it's obvious that it's correct. But how do you check that the result of an exercise is correct?
If the temperature is...
You redo the calculation 10,000 times and see whether you get the same or not. That's a possibility. It's a statistical check of the result. But how do you check in a smart way? You were saying?
If the temperature is 0, the energy has to be h or minus h.
Yeah.
And if the temperature is infinitely bigger than h, then it has to be proportional to t.
It has to be actually equal to 0.
If the temperature is...
If the temperature tends to infinity, it has to be 0. That has to be proportional to 1 over t. Right?
1 over...
To h over t.
h over t, yeah.
Yes. Anyway, so let's see. So what your colleague just said, let me rephrase it in a different way. In any problem, there are some limits in which the calculation is trivial. Or if the calculation is not trivial, you can guess the result on the basis of simple physical arguments. Okay? Then you take the result of your calculation, you go to those limits, and you see whether they match or not. Now, this does not guarantee that you got everything correctly, but you have to have bad luck. And in any case, if you check the limits and everything will be fine, you will get, and everything is fine, you will most probably get the exercises solved in the final exam, unless you made a very stupid mistake.
So if the temperature is infinite, all the probability of particles being at +1 and -1 is the same, so that
Yes.
energy is 0.
Yes.
At temperature equal to 0, all of them goes to the...
Yeah, if temperature is equal to 0, you are anti-parallel to the spin. You see the minimum energy state is sigma equal to -1, and the energy is -h. And it works indeed, because if h is positive, you see that if I send the temperature to 0, which means beta to infinity, tangent hyperbolic of infinity is 1, and therefore I get an energy -h. And if the temperature goes to infinity, beta goes to 0, and tangent hyperbolic of 0 is 0, and therefore everything is fine. Okay? Everything is correct. So the first exercise is essentially solved. There is another thing you can perhaps check, which is what is the magnetization. Magnetization is dF dH, and this comes out to be equal to minus the tangent hyperbolic of beta h. This is also equal to the average of sigma. And you see that everything is fine. I mean, if temperature goes to 0 is 0, if temperature goes to 0 is -1, if temperature goes to infinity is 0. Everything is cool. Great. So now let's do a second exercise. So in this exercise you learned how to write down the partition function when you have a generic statistical object, and in this case it was discrete, and that you have to compute the free energy once you have the partition function and take derivatives of the free energy, okay, if you want to compute physical quantities. And then if you want to check yourself, you take limits. Alright, so now let us do another exercise. Let us consider the following system. H equal to sum over I from 1 to n, H sigma I, where sigma I is equal to plus and minus 1. So it's just a bunch of spins in a magnetic field. All right? So what is the partition function? I know that you know.
It's the multiplication of all to the n, up to the n.
Fantastic. Is it clear to everybody? The partition function is just, you take the partition function of a single spin and you multiply it n times. Everybody sees this? Good. Everybody? Everybody? Someone is not convinced? Okay, good. No, it's important. Now, this property, that the partition function is the product of single particle partition function, is a property that is characteristic of non-interacting systems. Because for non-interacting systems, the statistics of each particle is independent to what happens to the others, right? And that's why the partition function is the product of partition functions. So in other words, we get that Z is equal, in this particular case, to sum over sigma equal to plus and minus 1 e to the minus beta h sigma to the power n, or in other words, is 2 to the n cosine hyperbolic of beta h to the power n. Okay? Good. Now, the free energy now is equal to minus n times t times the log of 2 cosine hyperbolic of beta h. If you look at it carefully, you see that this is nothing but n times the free energy of a single spin. And by the way, the fact that Z is the product of these guys implies that the free energy is extensive. You see it? Because the fact that this is this to the power n, when you put it in the log, implies that the n will come out to stay in front. Now, and therefore, if we now take the derivative, so if we now take the average energy, we'll get n times what we got before, so minus h times n tangent hyperbolic of beta h. Let's calculate something we did not calculate before, the entropy. So the entropy is what? The entropy is minus the derivative of the free energy with respect to temperature, right? Minus df dt. Now, if you do this calculation, what you should get is minus nh over t tangent hyperbolic of beta h plus kn log of 2 cosine hyperbolic of beta h. Now this is quite nice because, well, first of all, it's extensive and it's okay. Now, what do I expect in the limit in which temperature is equal to infinity from the entropy? What should it be equal to? You or not you, because I know that you know.
No,
Someone else. Sorry, but otherwise it's a. I can just ask.
I have actually no idea.
No, you don't. You don't?
Yeah.
You don't. Okay, he doesn't know. Someone else. What is the entropy of this guy at infinite temperature? Energy is equal to 0. Why energy is equal to 0? You mentioned it before. Why the energy is equal to 0?
Because this for a single,
For a single spin,
all of them, they can appear both. I mean, the probability for
the probability to be up or down is equal, right? Now, if I have n spins, for each one of them, the probability to be up or down is equal. And therefore, at infinite temperature, what is the number of configurations that I have?
2 to the power of n.
2 to the power of n, right? Because at the energy that corresponds to infinite temperature, which is equal to 0, the number of configurations that correspond to that energy is 2 to the n. Now, if you think for a second, let me draw a diagram. So this is the energy, this is minus nh, this is plus nh, this is the center, 0, and this is the point where you have most of the configurations that lead to that energy, to that result for the energy. You remember, there was another case in which we encountered something very similar to this. And I gave you to do an exercise with the computer in the first lecture. You remember? The central limit theorem? That everything was dominated by the points where you had the maximum configuration. So here, the diagram is very, very similar. If you fix the energy here, so if you fix temperature to infinity, the number of configuration is actually exponentially large and is maximum. It's 2 to the n. And therefore you should expect your entropy to go like n log 2. Okay? Does it happen for temperature going to infinity? Look at the formula. Is it happening or not?
yes. You will have the cos beta h will be like 1.
Absolutely. So you see, it happens because if temperature goes to infinity, this guy here is going to 0. This guy here is going to 1. And then I have up to k, Boltzmann, that I should not even write, because I decided that it's equal to 1. I should have n log of 2, which is exactly what I expect. Now, what do I expect instead when temperature goes to 0 from the entropy? What should the entropy be at 0 temperature? So, when the temperature goes to 0, you go back to what you know from the internal energy. The internal energy is going to be minus h times n. And then you ask yourself, how many configurations correspond to that energy? 1. All spins aligned. Okay? So you see the reasoning when you want to find the limits of the entropy. You ask yourself, okay, temperature goes to infinity. What is the average energy at temperature going to infinity? 0. How many configurations correspond to 0 energy? 2 to the n. The entropy is n log 2. Temperature goes to 0. What is the average energy? Minus h times n. How many configurations? 1. The entropy is log of 1, 0. Okay? Now, the entropy, therefore, is equal to 0. And let's see if it works. Well, it's not that straightforward, right? When temperature goes to 0 means that beta is going to infinity. Now, when beta goes to infinity, let me do it here. I don't want to turn page. When beta goes to infinity, now this guy here is equal to minus nh over t. This guy here, the cosine hyperbolic is dominated by exponential of beta h when beta goes to infinity, right? So cosine hyperbolic is approximately 1/2 e to the beta h, and therefore the 2 goes with the 1/2. You have log of e to the beta h. This is plus n. Log of e to the beta h is beta h. So times beta times h. This is equal to 0. K Boltzmann is equal to 1, okay? So you see that it works. So all of this to tell you, now life is extremely simple because we are doing super simple calculations. I mean, you know, my daughter is 2 years old. She does this after breakfast. I'm joking. We're doing super simple calculations. But if you, when you will do calculations that are more complicated, it's very important that you learn to check yourself systematically the way I'm telling you now. Okay? So it's really very, very important. So every time you do a calculation in physics, in theoretical physics, no matter whether it's statistical mechanics or something else, you get to the end of the calculation and then you ask yourself, is there a limit in which I can guess the result? And then you try to reproduce that limit, okay? By taking some parameter to infinity, to 0, to some value you know. You benchmark your result by some values that you know. And then you check yourself this way. All right. Now, in statistical mechanics, there is another way. By the way, there is another thing I wanted to do, which is interesting. Let us calculate, for this particular problem, the fluctuations of energy, right? Which is h squared minus average of h squared. Now, what is average of h squared? For this particular problem, average of h squared is equal to sum over I and j running from 1 to n of h squared sigma I sigma j, and then minus average of h squared, that is something we already calculate. Now, this is equal to what? Well, let's write it down explicitly actually. It's equal to sum over I and j from 1 to n h squared sigma I sigma j. Okay? Now this is equal to sum over I and j from 1 to n h squared sigma I sigma j minus sigma I sigma j. This object here is called a connected correlation function. That's the name it has in physics. Correlation function. What is the type of information it gives you? It tells you essentially the following. If I know that my spin here is up, I want to know what is the probability of the spin there to have a value that is correlated to the one this guy has. So if this spin is up, perhaps that spin there is also up. And if this spin turns out to be down, that spin there is down. If this happens, that when one is up, the other is up, the other is down, the other is down, then it means that the two spins are correlated, have values that are correlated. If this does not happen, so the value of that spin does not depend on the value of this spin, they are totally uncorrelated. Now, typically in physical systems, there is a range of space of, there is a length around each spin around which all the values of the other spins are correlated to this guy. And this is called the correlation length. We will see this in detail later on. But for this particular model we are dealing with here, we have just independent spin. So if we have independent spins, there is no interaction whatsoever. If this guy is up, that guy, okay, can be whatever he wants to be. He doesn't care about this guy, right? In other words, this correlation function is going to be equal to 0 unless I is equal to J, because of course I am correlated with myself, hopefully, sometimes. Okay? Alright. So, this means that this is going to be equal, sum for I equal to 1 to n of h squared, and then you're going to have sigma I squared, which is equal to 1. So 1 minus average of sigma I, average of sigma squared. And now, if you think for a second, this is going to be n h squared 1 minus average of sigma squared. So you see explicitly in this particular case that this, sorry, I wrote something wrong here. This minus h squared. So you see explicitly in this calculation that this quantity does depend on n, as I wrote down before, through this mechanism. Okay? We have a few minutes. Let us do another exercise. It's not an exercise, another example that, of course, is the ideal gas. So we have been dealing with non-interacting systems in this lecture. Let us do the prototype non-interacting system, which is just a bunch of particles with just kinetic energy in 3 dimensions. Okay? In this case, the partition function is the integral dq dp of e to the minus beta sum over I pi squared divided by 2m. As you already told me a few minutes ago, this is the product on n times of the partition function of a single particle, which is equal to integral dq dp e to the minus beta squared over 2m and to the power n, and therefore this is equal to v to the n divided by h to the 3n n factorial times integral dp x dpy dpz of e to the minus beta px squared plus py squared plus pz squared divided by 2m. But this is a Gaussian integral. We know how to do Gaussian integrals. So at the end of the day, we'll get 1 over n factorial v over h cubed to the power n, and then square root of 2m pi over beta to the power 3n. So this is my partition function for the ideal gas. Super simple, okay? It's not even comparable in terms of difficulty as to what we did for the microcanonical ensemble, in which life is much more complicated. Great. Now, given this, now let us compute the pressure, dF dV. Just a second. I'm wondering, how did I get this? Ah, yeah, sure, of course. I mean, if you do this, minus the FTP. So, once you're given this, you have to compute the free energy, minus T log of Z, kB T log of Z, And then you take the derivative of this free energy with respect to V and you compute what is the the pressure. I'll let you do the calculation. What you will get is kBT times N over V. Now you can see easily why this happens, because if you take the log, right, look at where the volume will enter. You will get a term that is N log of V. When you take the derivative of this, you will get N divided by V. And this is where this term will come out. The kBT is already in front, and everything is beautiful and fine. So the equation of state for the ideal gas is just encoded in a very simple way in the calculation of the canonical partition function. So P times T is equal to M K Boltzmann times T. All right. So we are essentially done for today. So next time we are going to start with the calculation of partition functions and statistical mechanics for models of this type. Now, this is called an Ising model, when sigma is equal to plus and minus 1. Now, there is a major difference between this and what we have done up to now. And the difference is that here you have some kind of interaction. In addition, because of the presence of interaction, you will have correlations between different spins. The correlation functions are going to be non-trivial, and so on and so forth. So I'm going to teach you ways to solve this kind of problems essentially in one dimension and in generic dimensions using something called the transfer matrix. And then we are going to move on with other models, Potts models, etc., etc. But you should see all of this as a kind of super session of exercises solved by me together with you. Okay? By the way, my student Silvia will soon start giving you some extra lectures, tutorials, homeworks, and things of this type to practice. Okay? She did it already 2 years ago. She will start doing it again. All right. So.